Good evening, we're Team DUCT, and I'm Scott, this is Erlis, and this is Zach. We also had David, but he's had to shoot off to Singapore. So the challenge that we chose was the PhoneSat, and this involved basically turning a smartphone into a micro satellite. And so we saw this as three main areas: the hardware of being able to turn a smartphone into a satellite, the software to run that smartphone, and then the software of an app or something that the smartphone actually does that's beneficial. And in the case of this project, it was a StarTracker app. So basically, you orientate the satellite to find where the stars are. So our approach, we chose to target the hardware side of this project and work out all the nuts and bolts of how that would work. And so our main idea was getting an Android or Ubuntu smartphone and then combine that with the Arduino to develop a satellite solution for mainly the hardware, but fully working solution. And again, this broke into three main areas: the power side of the satellite, how they'll keep running, the communication between the satellite and Earth, getting the data back, and also positioning the satellite in space so that it can target the correct stars.
Awesome. Okay, so here is our render of our satellite. As you can see, it's a box, and we've got the solar panels, which when it's launched is all compacted down. Then when it pops out the spaceship, the solar panels flip out, and you've got those two little small ones that flip out. We've got the antenna attached to those two small thin ones, and so that antenna is extended out for us. There we go. Here is our system diagram. So what we do is we got a smartphone. The smartphone, we utilized the earphone port, and we've got two little earphone leads. So we're using our right one to go off to the Arduino. It sends 3 coordinates down the wire to the Arduino, and the Arduino says, okay, I'm at this position. It's got a little gyroscope on it. It says, I want to get to this other position. It's got 3 vibration motors set on 3 different axes, so we can change all these rotations. So the motor spins one way, the phone spins the other way. Therefore, we can change the attitude of the phone the whole time. We then use the other earbud to communicate to a low-gain antenna. This meant that we could send photos to Earth and also receive information back saying, go to this position here, because we want to look at some stars. Finally, we used the 2 solar panels you saw on the previous slide, and the battery system inside the phone itself, so we could power the whole thing. And our solar panels developed more than enough power to power this whole thing. And now we've got a little demonstration. Now we were a little bit short on parts, and so I've got these LEDs here. So if you can see this, I'm also connected here. We've got an X-axis, a Y-axis, and a Z-axis. The green means that the motor is in the forwards direction, and so the phone is turning in the reverse direction. We also did not have a gyroscope to work with, unfortunately. And so I've got a little pot here which I'll turn. So say right now we're at this position and we want to turn to a different position. So the X-axis so the phone has to go in the negative direction on the X-axis, so the motor's turning in the forwards position. As it moves, this pot would turn, so the accelerometer would be changing where the phone is until, we've gone past it and it's gone to red. Now the motor goes in the opposite direction until we balance it, and now the motor's not going, it's in the right position. This will be happening simultaneously with the Y and the Z axis.
So in terms of collaboration, we had a chat with Fred Kennedy from CubeSat. This was mainly about the solar panels and whether the commercial solar panels that you can buy every day would work well enough in space. And we found out that they're quite inefficient, as he set up the 9 to 10% instead of 28%. And so we had to use this and take into consideration when doing our calculations for how much power we could generate and how much power we'd need to use. We also talked to a couple of other teams from around the world, one from London and one from in the States. And the one from London was particularly helpful in working out how to communicate between the smartphone and the Arduino, because it wasn't quite our expertise. And then the one in the States was focusing more on the app side, so we could make sure that whatever we're wanting the smartphone to do is actually possible, and it would be able to create a full solution if we combined ideas.
Alright, due to using off-the-shelf parts and a reduced profile for the satellite, the price point for launching a satellite into space has been brought down to the point where high schools as well as universities can launch their own satellites into space. That opens up things like competitions. So currently, high schools compete in robotics competitions, the first USA robotics competition. You could have a parallel type of competition which high schools have to launch satellites instead and do useful science.
2 minutes left.
Ooh, yep. So communities, this brings space and space science into the social sphere because everyone will know somebody who's involved in launching a satellite or who has an interest in launching a satellite. Commercial applications, because the price point has been brought down, the camera or other sensors which could be attached to the phone could be used to gather commercially valuable information. And there's also science, so basically there's a large group, a growing group of people who are called citizen scientists. These are people who put in resources to do valuable science, which actually ends up making discoveries and doing good things.
1 minute left.
This is an example for an interface using an iPad or an iPad app or also a website. And this could be either controlled through the website or iPad app, or it could be for third parties who are interested in seeing what these satellites do to have a look at what they're doing and their orientation and what they're looking at. So you have at the bottom where the satellite is positioned currently and the most recent photos they've taken. There's a huge social impact with reducing the price point for people accessing space and becoming involved in space exploration. It raises an entirely new generation of engineers and scientists who in the past created the computers that we use right now. Next step, so our example was with using a camera to do star tracking, but what could also be done is other sensors or potentially even motors for a rover on Moon or Mars could be used, and yeah, someone has to build it. Thank you.
All right, thank you. Questions from the judges?
I had two. One is you mentioned it's cheaper to get items into space now. I just was wondering what the actual cost and how accessible that is, and also your design had a fairly simple box. I'm not sure what it was made out of, but how is the instrument protected from cosmic rays that normal satellites have protection from? Thank you.
I just go back to that.
So the price point is roughly $10,000 for the entire launch and development and buying all the parts and everything. This is because you're using off-the-shelf parts, as well as the profile has been reduced. So you have your usual CubeSat profile in terms of width and height, which is 10 centimeters, but you have about a 1.5 to 2 centimeter depth. So that allows you to launch about 15 of these satellites in a 3-unit P-pod launcher. And in terms of the structure which protects it from the space environment, it's your usual CubeSat chassis, which has just been adapted to include a small profile. So your general suite.
Okay.
No, it's quite interesting. I'm just curious, so you said when you started out it was the hardware, the software, and the app, and I think I've got a pretty good idea, of how the hardware is actually going to work. In terms of the app itself, did you have any time or ability to go into designing that, or you're just saying just one of the more generic? Why did you pick the StarTracker app, for example?
So the StarTracker app was just part of the challenge that NASA provided. Okay. And yeah, so one of the other teams from the States was working on that. And so we thought if we can get the hardware side all sussed, and then they get the app all done, and then we could combine them all and have a finished complete product, because we sort of felt 48 hours for a whole solution would be impractical to get it all working, all feasible.
So do you think you'll continue with your project?
Yeah, Well, after we worked out that it only cost about 10 grand to send a satellite up, we were pretty excited. And yeah, it'd be pretty interesting to be able to do that. Yeah,
Building a working prototype would be cool.
yeah,
Without actually
definitely.
launching.
Yeah, with real motors instead of LEDs.
Just trying to understand the feasibility in terms of power consumption. Can you talk us through a little bit about that and you know, how the communication back to Earth works for a user and for data collection?
That's all you guys.
I'll
Yeah,
do power and you can do
yeah.
So in terms of the power, we calculated it would produce roughly about twice as much power than that will be used. But even worst case scenario, if it doesn't do that, the satellites in low Earth orbit are projected to be in orbit about a year. So after that, their orbit decays and they end up burning up in the atmosphere. So we easily found that it produces more power than is required because the smartphones have been designed to use very little power because they want the phones to last longer, etc. So they have very good low power electronics already in there.
And that includes the cyclone power for communication?
Yeah, that includes the power for communication there, and I'll just let him.
Yeah, and so in terms of communication, so the communication would be done through the headphone jack. So the headphone jack has two outputs and one input, and that's typically used for the left ear, right ear, and microphone. And so we're going to use the left-hand ear for communication reasons and the microphone for communication from Earth. And so the headphone will go to a radio transmitter, and then this will amplify using a low-gain antenna, send the signal to either other satellites that are used for relaying signals or directly to Earth. And yeah, so we worked out using a 10-minute pass time, so communication time, we could send up to 6 megabytes of data, and using file compression, etc., that could be about a dozen photos maybe. And then also, because it's an audio signal, it'd have to be encoded quite a bit. So the data would originally get encoded using frequency shift keying, and so what that is a change in frequency is read as a 0, and no change in frequency is read as a 1, and so it's just binary code that can get sent down to Earth for them to then interpret as images and data, information, etc.
Okay.
Yeah.
You're looking for investors?
Yeah.
Is it judging criteria? All right. Okay. Thank you very much.
Thank you.